Another of our Discovery Center projects, and Steve Thurbein, did I pronounce that correctly? Is the external supervisor on that, and our three workers, our worker bees, all right, Alexander and Betty and Khaled. And again, you guys know that you've got about 20-25 minutes to do your presentation, and then we're going to ask questions until you fall over. And then at the end of that, we're gonna clap, okay? And so you guys got about 20 minutes, and so we'll start the questions with you, and then by then Dr. Gould will be back, and he has questions from Dr. Palmereka, and then we'll open the questions to the floor and see if there's any of those. So you guys got about 20-25 minutes, so I'll give you sort of the 5-minute warning, and you know when to slow down. All right, thank you.
All right, so as Dr. Little mentioned, I'm Alexander, this is Bobby and Khaled. We built a hovercraft for the Discovery Center. Our external supervisor is Steve Thurbein, and our internal is Dr. Palmereka. So today we'll be covering materials and procedure, just talking about what we used and how we used it. We have a short video of the way to test it. We're going to be talking about how a hovercraft works. So Khaled will be covering the lifting, also the propulsion and control. We'll go over some of the safety features that we did implement and that we hoped to implement. And then we'll cover some recommendations for future work, as well as a short demonstration, and we'll cover any questions you guys have. So Body's going to talk about the materials that we use.
For our project, we divided into 3 parts: the base, the seat, and the control system. For the base, actually, we choose a circle base made of plywood with a half-inch wide, and we picked that wood because of the stability and the lightweight that it has. And for the skirt part, we made actually 3 layers of thick plastic, and that's in case we use the hovercraft at a bumpy surface. So if one layer gets ripped off, we can easily continue working on using those as the other 2 layers. And we use a foam pipe insulator, which actually we use it as a bunker. So in case our hovercraft hits someone or anything, won't do anything or won't hurt anyone, especially because it's mainly used by children. And for the seat part, we actually, to the budget issue, we used the same box that we were provided from the Discovery Center, and we added a cushion on it so it would be more comfortable. And we added the back because children usually might fall down and hit the rear leaf blower. And for the control system, we actually used 2 leaf blowers, one to blow the air into the skirt, and the other one to push the hovercraft forward. But we actually we were supposed to use a fan, and we thought that the leaf blower would be more efficient than the fan, because a higher efficiency fan has really high prices. And we made actually a control box. This control box has 4 main things: a button for direction, a button for speed, and a button for the buzzer and the switch. And I'll talk about the procedure, how we build it quickly. As you see in picture number 1, this is the circle base. We made it's 4 feet diameter, and we made a hole. As you can see, it's over there. It's for the leaf blower hose. And for the second part, this circle represents the skirt, as we put 3 layers down at the bottom of the base, and then we flip it, we stick it using staple gun and tape. And we used coffee lid can because to attach these skirts into the bottom of the hovercraft, and we used 4 screws to attach it. And we made actually 6 holes in the skirt, so when the leaf blower blows air, all the air will go from these 6 holes. And after that, we attach this hovercraft. This represents the hovercraft. And here, as you can see, the hovercraft blows the air into the skirt. And this is the skirt here. And the air will go out in the direction of the arm. And after we build it, we had a short video to see how it works and make sure it's working. You see here the hovercraft floats and then are flowing down. And this is the first test. So yeah. And Khaled will start here with the lifting force.
Here I'm talking about the electric force for the hovercraft. I want to start talking about the container pressure, which consists of the skirt, the bottom of the hovercraft, and the surface. There's all have pressure being applied to all of it. And well, because the pressure, the airflow goes through the hole of the underneath the skirt, what happens is it creates a force that's equal to the weight of the hovercraft. And this is going to create something called an air gap. It's called daylight clearance. And this air gap, what happens is it goes through creating pressure, maintaining the pressure in the skirt. It's through equalizing the flow and coming from the leaf blower and the flow coming out of the hose of the skirt. And this is a formula here to show the force, and the force here is being applied by the pressure multiplied by the area. And we know our area here is a circular, so we have a 2-foot radius polywood, which gonna give us like 0.56 foot square. And the pressure, we calculated the pressure by plugging the outlet of the leaf blower and measuring the pressure in there, and that gives around 30.8 pound per feet square. And this is approximately like equal to it's divided by 144 to equal to VSI. So basically VSI is equal to this number divided by 144 is going to give us around 0.21 VSI. And here because we know that the weight is actually a part of, it's actually the force and added the gravity component to it. So we can easily substitute the weight with the force, and we get 387 pounds. That's how much our hovercraft can lift up. And here, just showing like how it's equal to 0.21 psi, and this is showing like having 32 psi in our tires. How big that number is actually to lift up probably a heavy components. And here, Alex is going to talk about the propulsion.
So as Buddy mentioned earlier, we initially wanted to go with a fan in the back. It just seemed like the logical thing to do. But we found out that it just wasn't going to give us enough power. We're going to need a really big fan, and when you have a really big fan, you have a lot more weight. It's a lot harder to move around. And not only that, it's a little bit more dangerous. So what we decided to go with was a small scale leaf blower. So this, it was really well suited to our needs. It weighs just under 5 pounds. It puts out wind speeds of 260 kilometers an hour and puts out 170 some cubic feet per minute. So we could have gotten a much more powerful leaf blower for actually the same price, but it was bigger, and since it was a lot more powerful, it would have generated a lot more speed. And since this is intended to be used potentially by children, that wasn't really something we desired. We found that this leaf blower gave us just the right amount of speed. And not only that, it actually had 2 different speed modes built in. So as you can see there from the picture, we have just an extension wire running up to our control box, which runs to a 3-position switch so that we can get fast, low, and off. And the position of this propulsion fan is controlled by the servo. So essentially how the system works is the user will turn a knob on our control box, which will rotate the rear fan, or the rear leaf blower. And based on where that's pointing, it will provide force in different directions, and that allows the user to move around in the hovercraft. So here's the control circuit for the servo. It's based on a 555 timer. And it's put basically just in 555 timer in astable mode. So it's constantly outputting a pulse. This is a variable resistor here, and as the user changes the resistance just by turning the knob, that increases the time constant of this portion of the circuit. And based on that time constant, that's going to vary the duty cycle of our pulse. So we're varying it anywhere from 600, or ours actually goes from 800 to about 2400 microseconds. And ideally, to go from 0 to 180 degrees on the servo, we would go from 640. But we found that just based on the limitations of this formula, we couldn't quite get the exact range that we wanted. We did obviously implement or rearrange the formula and find just the right numbers, just the right capacitor, just the right resistors, so we could get very close to the range. So these numbers here are off on the scale, but basically that's our minimum pulse. It's a little bit noisy, but that's not a huge issue for the servo. It's an analog servo, so it's not sampling extremely quickly, so it doesn't really affect the performance at all. Yeah, so this is our wider pulse. It's almost exactly as wide as it needs to be, so that gives us a full 180, but we don't quite get all the way to 0 degrees. And there's also, as we vary the duty cycle, that's going to change the low time as well as the high time, given by that formula. But the low time isn't overly important. As long as the pulses aren't too close together, the servo doesn't have any trouble translating that pulse width into a position. So Bonnie's going to cover some of the safety features.
Yeah, as I mentioned about the shape, we choose the circle shape with flat pulses, it's not silver. And as well, I mentioned about the back of the seat, because it's mainly used by children, and we were supposed to use a fan when we found that it's really dangerous for children. And and as Malik said, we had an on-off switch in the control box. So basically, this hovercraft, even if you attach it to the electricity, you won't start unless you press the button. And we have a buzzer. It's like a horn to want someone that the hovercraft is approaching. But however, it's really noisy, so like this horn, like basically makes no sense. But we implemented, and we used a bumper as made of the foam pipe insulator, and already mentioned that. And we found that the hovercraft in general, after researching, it's really noisy machine. So this is the one advantage that it has. And Alex will go over some documentation I have these that we can go through this project.
So the major constraints that we dealt with were time and budgetary constraints. We were given a budget of $200 to $250. We actually, unfortunately, exceeded that. But anyway, so some things that could be done in the future is to add a seatbelt. We wanted to add the seatbelt out of a car or something, or not or something, out of a car. And basically the idea behind that was we would have it bolted onto the seat, and then when it was plugged in, most cars, most recent cars anyway, have a signal that determines whether or not the seatbelt is plugged in. So we could have used that, and what we wanted to do was use that to control a relay that would not allow the propulsion fan to turn on unless the seatbelt was plugged in. So although the hovercraft would lift, if the seatbelt wasn't plugged in, then it wouldn't be able to go anywhere, so that makes it just a little bit safer. Sensors could be added. Something like a distance sensor on the front could be used for object avoidance, and basically we would use the signal from that distance sensor to shut down the lift fan if it detected an object in front. And basically shutting down the lift fan is just going to drop the hovercraft almost immediately. So that would have been a really nice safety feature. We could have implemented an access control system whereby the user has to, for example, put in a password if they want to actually start the hovercraft, and that just prevents unwanted users from controlling it. Another thing that could be done in the future is a better control system. Basically, right now we're relying on the human brain to perform some pretty serious calculations, because the hovercraft is essentially a frictionless device. So when the user turns the control up, when the rear propulsion fan moves,